So I'm glad to present our next speaker. This is Evgeny Rodygin himself, and he will speak about a very important topic in Blend4Web and in real-time rendering in WebGL, and this topic is called simply optimization. So.
Okay, hello everyone again. My name is Evgeny Rodygin, and I'm one of the lead developers here on the Blend4Web team. And today I'm going to speak about a really hot topic, as we can see from the questions, I assume. So I'm going to speak about optimizations, and my presentation will be called Optimize Your Blend4Web Application. So all we, no matter artists or programmers, would like to create applications or scenes with beautiful visual stuff, with a beautiful picture. We spend decent amount of time, sometimes decent amount of money in order to create beautiful graphics. Here are some of beautiful projects made with Blend4Web. Well, we spend all this to create graphics, and sometimes we find ourselves in a situation when we push it all to the web with the help of Blend4Web, and it appears to run at, say, 5 frames per second, or maybe even less. And this is absolutely not acceptable for us. So another name of my presentation can be the battle between beauty and speed. Okay, here's a short plan for my presentation for today. First of all, we'll try to understand what causes an application to run slowly. So we'll discuss the Blend4Web features, which are the most difficult on particular parts of our PC. Next, we would find the way to determine the bottleneck of our application, and I think this is the most important part. Many guys already asked about it previously, so this is the main point of my today's presentation, I think. The third point would be what can be done by an artist in order to improve the performance. And at last, I'll give several tips, not much of them because it can be another presentation. I'll give some tips on the programming side of the question. So what can programmer do in order to improve the performance? So first of all, when we speak about graphics, and when we speak about 3D graphics, we generally have GPU and CPU on the left hand, which are responsible for drawing the exact picture on the screen. And we have a developer on the left hand. He is, in our case, a bad guy. Why? Because he pushes visual content to the GPU and CPU. And in case of 3D graphics, and especially in case of 3D graphics in web, there can be lots and lots and lots of visual content. And our today's job is to reduce this amount and to leave the picture as it was before the optimizations. So, which features are the heaviest on CPU? First one, and the most obvious, if we have too many dynamic objects, it will be a real pain for the CPU. The next one, too many different materials. These 2 points are closely connected, and we will discuss it a bit later, why is it so. The next, shadows, the real evil of 3D graphics are for me. So this is also connected with the first two. The next, dynamic reflections, kind of similar to shadows, and this is really important when we use cube reflections. Because, yeah, you know, we have in Blend4Web 2 types of reflections. Plane ones, which are reflected from the plane objects, and cube reflections. in case of cube reflections, in the worst case, we need to redraw the object 6 times. So cube reflections are really heavy, feature technique for the CPU. Now, global particle systems. Why are they so slow? Because they initiate the information exchange between CPU and GPU, which is kind of the biggest deal for the 3D graphics at all. So, and this restriction will stay with us until the full implementation of WebGL 2.0. Actually, my colleague Ivan Lubovnikov will tell you about it much more in his presentation. So, after WebGL 2.0, things will be much better at this point. And the last one is physics. Yeah, though Blend4Web uses kind of optimized approach for physics, we run it in a separate thread with the help of so-called web workers. Maybe someone of you, I'm sure you are definitely familiar with this term. Yeah, and this is a really important point for mobiles. Why is it? Because at the moment web workers are not really well implemented in mobile web browsers, so physics are again a great pain for the CPU in case of desktop PCs and in case of mobile phones especially. So the first 4 points can be described by the term draw calls. Yeah, I'm sure some of you should definitely be familiar with this term. So the more of these 4 points we have in our application, in our scene, the more draw calls we produce. So minimizing this will minimize the amount of draw calls and will make the life of our CPU much easier. So now about GPU, Graphics Processing Unit. Complex materials. Yeah, the more complex materials we have, say some node structures, some mathematics inside nodes, lots of texture lookups. Well, the more complex shaders we achieve, we get. So, and this is bad for GPU. Yeah. Next, post-processing effects. So, these two are closely connected. Why? Because post-processing effects also produce kind of heavy shaders. So they give a lot of work for the GPU. So maybe even if you create a really simple scene, say place only one cube or maybe one Susanna, and then you will turn on all the post-processing that Blend4Web offers. For example, anti-aliasing, bloom, kind of guard rays, screen space ambient occlusion. This is the baddest thing, I think. Then you can find that your scene runs at the above described 5 frames per second. So use post-processing really carefully. Shadows, yeah, they are here as well. So shadows can be painful for both CPU and GPU. In case of GPU, the worst thing you can do with shadows is to increase its resolution to, say, 4 or maybe even 8K. I mean, the high resolution for shadows we have, the bigger job GPU makes. So, too many transparent objects. Why transparent objects are really heavy on GPU? Let's compare opaque object and transparent one. In case of opaque object, we do not need to render something that is placed behind this opaque object. And in case of transparent objects, we would draw everything that is placed behind them. So if you place one by one, say 100 transparent objects, all of them would be drawn by the GPU. So use blend, add, and other transparent objects with really carefully. And the last one and the most obvious may be many lights. So the more lights you place on your scene, the more work on shaders you will get. So all this can be described by the term shaders. Yeah. So minimizing these 5 points, maybe there can be something else here, but these ones are the most important ones. So minimizing this minimizes the complexity of shaders. Yeah, and now the most important point of my today's presentation. How can we determine the bottleneck? Here's a really, really simple diagram. You need to find out what is causing your application to run slowly. I suggest you to open it in the viewer application, then disable two features which have a big impact on the performance. GL debug, it was introduced only in this release, so you can turn it off. And outlining overview mode. I will show you it, of course, I will show you it a bit later. Then run the profiler. In our case, I will be showing you everything in Chrome browser. So then we run the profiler, and we can say from maybe 2 or 3 lines of its output, what is causing the biggest problem, the CPU or the GPU. Then, when we find out what is the matter, in case of CPU, we should use our HUD, which is built-in viewer application, and take a look at the render calls graph. In case of GPU, we should take a look at the time which is spent on particular scene parts. Yeah, that's it. Now I should show you several live examples, in order to understand how this simple diagram works. Yeah. Nice, yeah? We have 400 of Susannas here, an army. Okay, and 2 scenes, many draw calls and 1 draw call. They are similar visually. But in case of many draw calls scene, we have a little flag on each Susanna for dynamic objects. So in this scene, all Susannas are dynamic objects, so they can be controlled separately. And in case of the second scene, we do not have such flag. So first of all, let's try to export the many draw calls scene. I forgot to mention one very, very important thing. Let's close Chrome and open it with a special flag, which can be really useful when you are profiling your application. So I'm doing it all in Linux, but it will be similar on any other operating system. So the flag is called disable GPU sync. So we're disabling the vertical synchronization, so we can go above 60 FPS. Okay, now export it. And here we have, say, 320, maybe 30 frames per second. And we have 400 Susannas here. Let's take a look at the upper right corner. We have 401 draw calls here. So how we can check it? We select one Susanna and we can move it. Yeah, they all are separate objects. Okay. Now let's implement the above described diagram. So how to determine which is the worst thing for our scene? Well, and please mention the FPS immediately drops to 180 when I moved camera a bit backwards. So, no, I forgot how my diagram works. Okay, we disable the GL debug feature. It is placed in tools and debug section. We disable it. So now we have more frames per second. Okay, and disable overview outlining mode. Yeah, for fair measurements, let's take a look at this number. 500. Oh, it's too much. Okay, something like 500 frames per second. Now let's open the Chrome profiler. Don't be afraid of the console. So we need this section, profiles, and just start it. Start profiling the CPU information. Stop. And what we have here. In case if we are artists, we need to look only at this one line. idle. It is called idle. So it shows how much time, how free is our CPU. It is not really free. It makes a lot of work. So we can say from this that our application is CPU bounded. Okay, you can see that other points taking much more time. So our application here, our scene is CPU bounded. Okay, that's it. Now we're going further by our shim. So we are CPU bounded, and we have to look at the render calls section in the HUD. Where is the HUD? It is also in the tools and debug section. Here, HUD info. Turn it on. And yeah, we need to take a look at the render calls. Here it is, 400 render calls for the main APAC subscene. Yeah, I need to mention here, we use a special term, kind of abstraction, to describe particular parts of our scene. We call them subscenes. So main APAC is the subscene which draws APAC objects. So we have 400 draw calls. Yeah, we can say it from this section actually, but in case of complex application, we better run HUD. So we need to minimize the amount of draw calls for such application. Okay, that's it. Let's turn off the HUD application and go back to our scene. Now we export the one draw call scene. And here we have, lots of frames per second. And all these, and it even doesn't go below this amount when we move camera backwards. So, okay, let's run the profiler. That's it. The amount of idle is really higher. So our application is GPU bounded. That's it. Open the HUD and take a look. Well, even if it runs very fast, we can anyway profile it. So, okay, maybe that's not the best example. Okay, I'll show you some more later. So the most of time is going to the main APAC scene, obviously, but also the anti-aliasing, the post-processing which I described previously, is taking its part. Okay, another scene. Many materials. No. Many materials. It's very, very, very simple. It's one object. Yeah, with 16 materials applied to it. A really bad technique. But okay, this is only for demonstration. We export it. And we have 17 draw calls, separate draw calls for each material. So if it is possible, try to avoid such situations. Maybe if you can use vertex colors painting or maybe textures, use them instead. Because having such setup is really bad for the CPU. Okay. And the last scene, no, this one I won't show you. Again. Shadows, my best piece of art. Okay. We have 4 dynamic lights here. Yeah, and all of them, they are casting shadows. Yeah, and in the shadows section in the rendering, we have resolution set to 4K. Okay, let's take a look at it. HUD is spoiling the picture. Yeah, that's it. Many, many shadows. I forgot to turn on the flag. Okay. It forget me already. Yeah. And we have something like 400 frames per second, maybe a bit more. That's it. Yeah. Let's open HUD. And we have here a shadow receive subscene, which is causing the biggest work for the GPU. Yes, and all these shadow cast subscenes are also having their impact. So this scene is CPU bounded. Yeah, I can show it, but I think you can believe me. It is what I said, GPU bounded. Yeah. So shadow receive is the biggest contributor for the performance here. Okay, let's close it. Oh, no, we won't close it. And change the resolution to 512. Take another look. Yeah, we need to measure the performance. Now it is not much bigger, but almost more than 700 frames per second. And we have kinda blurry shadows. Someone can find it even attractive. Okay. Yeah. We reduced the resolution of shadows, and now in the HUD application we can find out that the time spent on the shadow receive is less. And shadow casts are causing almost no impact on the exact performance. So we optimized our scene really well. If you like blurry shadows, this can be combined in order to get a better optimization. Yeah. Okay, I think enough examples. How much time do we have? Plenty of time. Okay, then I open one more scene. No, not this one. Lots. I'm in a Blender game profile at the moment because only it shows the level of detail changes. I have a setup of 3 loads here. You can see it in the object section. Susanna 1, Susanna 2. Yeah. And when I'm far from the Susanna, it goes really low resolution. So we export it to the Blend4Web. And we can see that from the distance, well, not to say it has no differences, but if you will set up, the loads more precisely, you can get much better results. So this is a really good technique to optimize your performance. Maybe this can be even applied for the photogrammetry. I don't know. Maybe. Yeah. Okay. Now let's go back to our presentation. Sorry. Yeah. So, few suggestions for artists. I'm not an artist, maybe. Oh, come on, yeah. Okay, what artists can do? First of all, the above described technique, level of detail. This is a screenshot from the Pythagoras tale assets. Someone can say that this is kind of gaming technique, but this can be applied in any kind of application which uses active camera movement, wide terrains. So it can be used wisely and give a really good results. Really good results. So another suggestion: bake everything. This doesn't necessarily have to be cakes, but you can bake textures or even whole materials. So you can bake their shadows, some reflections. I don't know, maybe. Okay, bake everything. Now reuse existing materials. You have seen what can we get when we use different materials on one object. We have 16 draw calls instead of one for this that simple sphere. And if we use only one material for the whole scene, it can be drawn into one just in one draw call. So if you are CPU bounded, it is a really good idea to use one material for the whole scene. Okay. Use static reflections and shadows. So instead of using cube reflections, well, if it is possible, you can use mirror maps. So sometimes it doesn't really it doesn't have a really big difference. So maybe user would not notice if you use static reflections. So but this will save a big amount of CPU and GPU, both of them. I mean, give us a lot of performance. Okay, and about programming side. There are just several tips. I said already that this can be another topic, but these ones are the most important ones for me. So the first point can be achieved by the cooperation of artists and programmers. So divide scene into parts for dynamic loading. Actually, Misha was already talking about it in the Pythagoras tale example. Dynamic loading can give a real benefit for the performance when you can divide your scene to parts. Say something similar was done in maybe Morrowind or other games like that in the past, and actually it is done nowadays. So you can drop the unnecessary objects and draw only something that you need at the moment on your scene, and upload something necessary at its own moment. Okay. Sometimes when you are GPU bounded and you have no other options, it can be a good idea to just reduce the canvas resolution. Yeah, we are in the web, so we can do this and do not allow the user to expand the canvas. So just reduce the canvas resolution. As of physics, when we are bounded by the CPU and you find out that the biggest evil is physics, then we need to take a look at the real good instrument, the real good tool which built in Blender. This is collision groups. So carefully track which objects collide with which. So this can save a great amount of the CPU performance. And kind of tricky one, the fourth one. Sometimes you need to track the position of some object on the scene in real time. You want to, pick this object from the screen, from the screen boundings, every frame. The first thing that comes into your mind is just to use pick object method from our API. But this is a really, really bad idea. Why? Because it forces GPU to send information back to the CPU. It is a killer feature, So what I suggest instead of pick object is to use physics. You can just use a physics primitive on an object and cast rays from the camera and track an object this way. It will be much, much more faster. So this is a really tricky one, but an important. We faced it in Pythagoras tale as well. Yeah. Thanks for your attention, guys. I hope you would have some questions.
Any questions for Evgeny, please? Okay.
Eugen, tell me please, how many levels of detail we can use in the one scene?
You mean for one object?
Yeah.
I have no idea. It is up to Blender. Misha, how many loads can we use on one object? Okay, infinite. We have unlimited possibilities in this way. Yeah.
Okay, thank you.
Yeah.
Any questions, please? Mm-hmm.
I don't know if it has been fixed or modified or I can just use it, but I didn't manage to use load on objects groups linked to a particle system. So I have objects on the library and the group is linked in the scene. In the scene there is a particle system that spreads
Yeah, I see. You mean hair particles, yeah? Hair.
like hair particles or just dot particles, and I use to render the group on every.
Yeah, as far as I remember, we do not support loads at the moment. Yeah.
Okay.
But it is in our plans, of course. Yeah. This would be a good
Thank you.
optimization, yeah.
Thank you. Any questions, please? No question? Huh? Got a question.
questions?
Hello, Evgeny. Thank you for your talk. I have several questions. First of all, in a hard times, what exactly are those? What is measured and by which mechanism? Is date now, performance now, and what exactly is between start and end? It's just draw calls? Or
Yeah, in case of GPU, this is a really different approach. Recently, Chrome browser, I don't remember about Firefox at the moment, they supported a special extension which is called joint.
Disjoint time query. I know about the question. I actually gave a talk on Bottleneck and Highload++ 2015 about it. I'm asking about it because you these numbers are pointless because
No, they are not.
Yes, they are.
No, they
because
are not.
they are because of two things. First of all, you still don't send me what are they measuring, and second of all, if they measuring only draw calls, yes, they are, because draw calls are not blocking, and it's just taking one object, serialize it, and send it to other process, which is not representative of anything literally in the performance of GL application. That's first of all. Second of all, why don't you use timeline? Because it seems that the rendering of GL scene can considerably increase composite times. So you need to take into account.
What do you mean by timeline?
There is another tool in Chrome for profiling of GL application.
Yeah, of course,
it's considerably more comprehensive. It's
I'm speaking in case of artists are going to use my technique. Yeah, of course we can use timeline, but this is more of a JavaScript. So we only need to determine if we are bounded by the CPU or the GPU. In this case, profile would give us the exact information.
And also, I have a question about your frame counter, which also wasn't visible on screen. Do you measure frequency of request animation callbacks calls, or do you have some fancy mechanism to measure draw call, to measure frames per second?
We measure the length of the request animation frame. Yes, that's it, frames per second.
Do you know that between two compositions, two actual frame renderings in the browser, you have 3 or 2 request animation frame calls?
It wasn't me who implemented the exact measuring mechanism. Maybe Alexander can tell some more about this stuff, because it was actually his point.
I think that our approach is a good approximation, because compositing always should be in sync with JavaScript thread. So we can calculate and average our time spent on JS drawing, and so it will be correct, I think.
I tend not to.
It's possible
not to put
that
a lot of faith in.
It's possible that 2 or more draw calls will happen during one composition cycle, but in general, composition should be in sync with JavaScript thread. If you say draw something,
there is no such restriction like anywhere. Moreover, in, for example, Firefox, WebGL class is triple buffered, so it doesn't need to be in sync with composition like at all. It's very tricky question. I
Yeah,
know.
no,
I spent
If you
hours researching these problems, reading source code of browsers, reading.
by sync,
lists
I
and-
mean, by sync, I
I'm,
mean,
I'm maybe sounding a bit rude, but I'm just very interested what you know about it, what you dig up, what you use in a everyday optimization routines and something like that, because it's a very, very
Tricky,
big
yeah.
issue for me and for a lot of people out there, I think.
mm,
Okay, and
Okay.
I have a last question, and I think we can extend the discussion of it. Do you use any like real profiling and debugging tool for graphics, such as Adreno SDK, PowerVR SDK, DirectX debuggers, or something like that, to debug the browser itself with its contexts and see what really happens in hardware in a browser
GPU
between.
side, yeah. No, we actually didn't use them, but I think timeline and tracing, you know, from
Который
tracing
VTF,
utility.
который web tracing framework.
Yeah,
Yes.
about tracing framework gives us pretty good results, and I think we can rely on them. Yeah, of course. It shows compositing process, GPU calculations, and JavaScript thread calculations. So it's all there, and I think it's enough to get first impression on how the things are happening, and that's.
Okay, thank you very much.
Thank you.
We have question.
Yes, and we got one question from online chat, and the question is: are you going to do some JavaScript? I mean, exported scene compression in JavaScript, so that the scene, as I understand this question, the scene is compressed and then unpacked on web application with JavaScript.
With JavaScript. Well, maybe the author is speaking about obfuscation. No, how do you think?
Well,
I'm not sure. We use an obfuscation mechanisms when we compile project, so it significantly reduces its size. But in this case, of course, you need to use the project. So not necessarily, but the best way to compile a project would be to use the project manager. So, and you can dramatically decrease the size of your application this way.
I can also add that for exported scenes, we got native mechanism in the web is using gzip. This is a mechanism of compression all assets which are loaded into browser, so you can enable compressing in your web server and enjoy it for free. So no need to do additional JavaScript processing in this way. Okay, thank you.
Thanks.
Thank you, Evgeny.